Hello friends, welcome to today's lecture, and in today's lecture we'll continue our discussion. In previous lecture we have considered the variational problem with the constant this. Now in today's class we extend our discussion when this constraint is not only this finite equation but a set of equations here. So we have y1 dash to say yn dash is equal to 0 here, I is from 1 to say m, here m is less than n, and try to see that how to find out the extremal functions of this variational problem provided these constants are given. So let us consider here. So in the as I pointed out in the preceding section, we examined the problem of investigating the function for an extremum v equal to x naught to x1 f of x y1 to yn y1 dash to yn dash d of x, satisfying the boundary condition given at the end x naught and given at the end x1 as yj x naught equal to yj naught and yj x1 is equal to yj1 for each j is equal to 1 to m. And here we have discussed that we have a constant given in this form yi x y1 to yn equal to 0, I is from 1 to m. But now let us consider the constant in place of finite constant. Let us consider the set of differential equations. So here constants are set of differential equation phi I x y1 to yn y1 dash to yn dash equal to 0 for I equal to 1 to m. Here m is strictly less than n. So this type of constant are called non-holonomic, and the constant defined here are known as holonomic. So this we call as holonomic constant and this we call as non-holonomic constant. So in this case we will prove a conditional extremum of a function v is achieved on the same curve on which it is achieved an unconditional extremum of the function here. So as we discussed in a previous case, we also show that the extremal conditional extremum of v achieved on conditional extremum of this v bar. So here we define a new functional f bar as f plus I equal to 1 to m lambda x phi of I, and here we assume that these phi I are independent to each other. It means that we are assuming that Jacobian of phi 1 to phi m with respect to y1 dash to ym dash is not equal to 0. So here we are relabeling our variable in the sense that this Jacobian of phi 1 to phi m with respect to y1 dash to ym dash are non-zero, and this also guarantees the independence of the constant. So here we try to proceed in a similar way as we proceeded in a previous section here. So here let us take y1 to yn be an arbitrary permissible system of function that satisfy the constant equation phi I equal to 0 for each I equal to 1 to m. Now here we vary the constant equation and we have this j equal to 1 to n double phi I by double yj delta yj plus summation j equal to 1 double phi I by double yj dash delta yj dash equal to 0 for each I equal to 1 to m. If you remember in previous case this term is not coming, so this term was not there in previous discussion. So as we discussed there, what we try to do here, we multiply by say each term by lambda I and integrate from x naught to x1, and we have this x naught to x1 lambda I x summation j equal to 1 to n double phi I by double yj delta yj dx plus x naught to x1 lambda I x summation j equal to 1 to n double phi I by double yj dash delta yj dash dx equal to 0. So again we have the addition of this term. So here we simplify the second term by transferring the derivative on this term. So for this we integrate each term of the second integral by parts and taking into considering that delta yj dash equal to delta yj whole dash, and variation at the point x naught and x1 is simply 0. And so by doing this, we have this condition x naught to x1 j equal to 1 to n lambda I x diver phi I by diver yj delta yi delta yj minus d by dx of lambda I x diver phi I by diver yj dash into delta yj dx equal to 0. Now we will proceed further. So now let us consider the functional here. From the basic necessary condition for an extremum, delta v has to be 0, which reduces to this condition x naught to x1 j equal to 1 to n f of yj minus d by dx f of yj dash delta yj dx is equal to 0. This we obtained from this, that delta y is equal to this x naught to x1 j equal to 1 to n f of yj delta yj plus f of yj dash delta yj dash dfx. So by transferring this derivative on this, we are getting this equation number 2. So adding term wise all the equation 1 and equation 2. So here we have this equation 1 which we obtained from the constants, and this which we obtained by necessary condition for extremum, that is delta v equal to 0. So here we add term by term, and we get this notation f bar equal to f plus summation I equal to m 1 to m lambda I x phi I. Then this equation 1 and 2 can be written in a concise form as 3. So here 3 is what, x naught to x1 j equal to 1 to n f bar yj minus d by dx of f bar yj dash delta yj dx equal to 0, where f bar is defined as f plus summation I equal to 1 lambda I x phi of I. Now again this variation delta yj, j is from 1 to n, are not arbitrary. We cannot use the fundamental lemma. So here as we done in a previous case, we choose m factor lambda 1 to lambda m, so that they satisfy the equation f bar yj minus d by dx of f bar yj dash equal to 0 for each j equal to 1 to m. So this we did in a previous case also. The only difference between this case and the previous case is that in previous case this is resulting into system of n linear equation, but in this particular case this will reduce to a system of n linear differential equation in lambda I x and d lambda I by d of x. So this is the only difference between the previous case and this case, and since it is a linear differential equation and the involved functions f or phi all are continuous, so we have existence guaranteed. So and we can say that which has the solution lambda 1 to lambda m, which depend on m arbitrary constants. Now with this choice of lambda 1 to lambda m, now this previous equation number 3 is reduced to from m plus 1 to n, and we can say that it is x naught to x1 summation m plus 1 to n f bar yj minus d by dx f bar yj dash delta yj dx equal to 0. And here the variation delta yj j from m plus 1 to n are now arbitrary, and hence by assuming all variation except 1 as 0, we can apply the fundamental lemma, and we can get from the Euler equation that f bar yj we can get equation f bar yj minus d by dx f bar yj dash equal to 0 for j equal to m plus 1 to n. And so if we combine equation like this, which we have obtained by choosing factors lambda 1 to lambda m with this condition here f bar yj minus d by dx f bar yj dash equal to 0, which we obtained by applying the fundamental lemma. So now this will reduce to this, this will extend to this f bar yj minus d by dx of f bar yj dash equal to 0 for j equal to 1 to n, along with the condition phi I equal to 0 for I equal to 1 to m. Now these are n plus m equation, which is sufficient to provide as the solution y1 to yn and lambda 1 to lambda m. So it means that the function y1 to ynx that render the functional v a conditional extremum, and the factor lambda 1 to lambda mx must satisfy the system of n plus m equation, which is given by this and this. it means that they must satisfy the Euler's equation of the auxiliary functional V bar, which is regarded as functional dependent on the n plus m function. So if we consider V bar as a function of this y1 to yn and lambda 1 to lambda m, then these n plus m equation can be obtained through the Euler's equation applied on this V bar. So let us go to a new problem, and if you look at this analysis is similar to the analysis which we have discussed in previous case. The only change from previous study and this study is only these points. Let me remind you. One addition is here, right? Another addition is here in the in terms of equation. So here we are getting a differential equation rather than simple finite linear system of linear equation, and rest are almost same. So now let us move to a new problem, that is isoperimetric problem, and this we have already studied. The only difference between these previously discussed problem here, that in first we have considered that finite equation, conditions are given in terms of finite equation, and now we have already discussed the case when constants are nothing but system of differential equation. Now in case of isoperimetric problem, your conditions are given in terms of integral equation. So here we have x0 to x1, we have gi, say x y1 to yn d of x equal to 0 for each I equal to 1 to m, m is less than. So this also can be reduced to previous case by just assuming not 0, some value, say lambda li. So this can be reduced to this. So problem of extremum of this along with this condition are known as isoperimetric problem, which we have already discussed. But here we can observe that this problem can be reduced to the problem which we have just discussed by assuming a new variable, that is zi, as x0 to x, say gi x y1 to say yn d of x. So by here we can say that zi x0 is simply 0, and zi your x1 is given as L of I. So what is the advantage of considering this zi? That if we differentiate with respect to x here, then we have zi dash x is equal to g of I x y1 to yn. This I can write it as zi dash minus g of I x y1 to say yn is equal to 0. So if we denote this as say phi I, then this isoperimetric problem is reduced to the problem of finding the extremum of this functional along with this conditional extremum. Okay, so this we can solve. So taking this as phi I, we can apply our discussion which we have just done over, and we can find out say the solution of the isoperimetric problem. So and we can see that to obtain the necessary condition in an isoperimetric problem involving finding an extremum of a functional v, which is given as x0 to x1 f dx, given the constant x0 to x1 fi dx equal to li, I equal to 1 to m, it is necessary to form the auxiliary functional v double star, that is x0 to x1 f plus summation I equal to 1 to m lambda I fi d of x, where lambda I are constant, and we can write the Euler's equation for this functional v double star. This we can obtain from the previous discussion. Excuse me. The arbitrary constant c1 to c2n in the general solution of system of Euler's equation and the constant lambda 1 to lambda m, we can obtain these by the boundary condition and boundary condition defined at both the end, and from the isoperimetric condition, that is x0 to x1 fi dx equal to li from I equal to 1 to m. and the system of Euler's equation for the function v double star does not vary if v double star is multiplied by some constant factor. So it means that if we have already find out the extremal functional for v star with the v double star, then extremal curve will not change if we multiply by some non-zero constant, that is mu naught, and we can say that mu naught v double star equal to x naught to x1 summation I equal to 0 to m mu I fi dx. So what we try to do here, let us consider here. So so what we are doing here, we are having problem this. We are considering this problem along with this condition. So for this we consider v double star as x naught to x1. We call this as f plus here we have lambda I, summation lambda I, you can write it gi, I is from 1 to m and d of x. So here we consider this as f bar, and we simply find out the Euler's equation for this. Now if we multiply both sides by any constant say mu naught, then also there is no change in solution of Euler's equation. So what we can do here, we rewrite this as some integral x naught to x1, and you can write this as I equal to 0 to m rather than from starting from 1 to m, and we can write this as say mu I, and you can write it your fi and d of x. So here your f0 is your f, and your fi is your gi, and your mu I is equal to lambda I mu naught. So here we can simply write that mu naught v double star is given as x naught to x1 summation I equal to 0 to m mu I fi d of x. The purpose behind doing this, that now this is symmetric in all fi, and we can say that so here f naught is f and mu j is lambda j mu naught for j equal to 1 to m. The purpose is that now all the function fi enter in a symmetric manner, and therefore the extremal in the original variational problem and in the problem involving finding an extremum of the functional x naught to x1 f of s d of x given the isoperimetric condition x naught to x1 fi dx equal to li, where I is from 0 to s minus 1 comma s plus 1 to m coincide. It means that coming back to this, the purpose behind doing this is that if you look at we want to extremize this functional along with this condition, and for that we have seen that the extremal functional basically satisfy the Euler's equation corresponding to this variational problem, this functional. So here we can say that that out of these m plus 1 functionals, we can say that let us extremize say let us see extremize x naught to x1. You can take out of these fi from 0 to m here. You can take any say function, let us say that you take f of s x y1 to say yn and y1 dash to yn dash t of x. We want to say let us extremize this, let us call this as v of s here, keeping others as conditions. So we can say that now conditions are reduced as x naught to x1 x naught to xn f of I x y1 to say yn and y1 dash to yn dash t of x equal to li, where here I is running from 1 to say s minus 1, leaving this s out, s plus 1 to say m. So it means that here you can take you can extremize any of the integral keeping all other integral as constant. Then also your extremal functional will not change, and it will in all these cases your functional you have to form this kind of function, and your extremal functional functions will has to satisfy the Isosceles equation corresponding to this functional v mu naught v double s star. So this property is known as reciprocity principle. So here we discuss the first example, which says that show that then an isosceles triangle has the smallest parameter for a given area and a given base. So here we try to use the reciprocity principle to solve this particular problem. So we try to solve this problem by saying that a triangle, isosceles triangle having the given parameter and a given base has, say, maximum area. So if you look at here, let us take the base is already given. Let us say that this base is given as a of a and b, and parameter is fixed here. So let us say that parameter is some kind of L. So and we want to find out, say, triangle having the maximum area, and we try to show that triangle is an isosceles triangle. So what we try to do here, let us consider an ellipse whose foci are situated here, and keeping this AB as major axis, and let us consider this as y axis here, and let us consider this as the parameter, this plus this is the parameter here, and vary this, and we can have an ellipse kind of figure here. So here you can say that by the property of an ellipse, if we take any triangle keeping the base point as AB, then the area per parameter is going to be same. So we can consider this as P, you can say that Q, and you can consider this R. So we can say that the parameter of PAB, QAB and RAB will be the same. That can be shown in a with the property of an ellipse. But the area of this AQB is going to be the highest. The reason being that this is the having the highest say height. So this AQB will have the highest AQB will be a triangle having the maximum area because of it is having the highest height. So we can say that this AQB is the triangle having the same parameter but having the maximum area. So this can be considered with the help of reciprocity principle, that given that isosceles triangle has the smallest parameter for a given area and a given base. So with the help of reciprocity principle, we can say that isosceles triangle has the smallest parameter for a given area and a given base. Now moving on to second example. Here we want to find the shape of an absolutely flexible, inextensible, homogeneous and heavy rope of a given length L suspended at the points A and B, and the rope in equilibrium takes a shape such that its center of gravity occupies the lowest position. So we try to find out the shape of such a rope. So here we use the condition that in equilibrium position the shape it will any rope will take a shape such that its center of gravity occupies the lowest position. So we need to find out the minimum of y coordinate of the center of gravity of the string given by this. So I of y of x is given by x1 to x0, x1 to x2, y of under root 1 plus y dash square d of x divided by x1 to x2 under root 1 plus y dash square d of x, keeping the constant x1 to x2 under root 1 plus y dash square d of x equal to L. So this constant tells you that the length is constant and it is given as L. So we want to find extremize the functional this, keeping this constant in mind. So here we want to this implies that we have to minimize the numerator of the right hand side of 4 subject to 5. So we want to minimize the this numerator, keeping this thing as constant, that is L. So here we form the functional I star, that is x1 to x2 y plus lambda under root 1 plus y dash square d of x, and here lambda is a constant. So if you look at if you form the Euler's equation for this, then f is given as y plus lambda under root 1 plus y dash square y dash square. Now here f is independent of independent variable x, so here your Euler's equation reduced to f minus y dash f of y dash equal to constant. So constant, let us say c1. The f is y plus lambda under root 1 plus y dash square minus y dash. Now f of y dash will be what? Y plus lambda, and here we will get 2 upon 2 into 1 plus y dash square, 2 of y dash is equal to c1. So 2 will be cancelled out, and here we can say that y plus lambda, then multiply here, so we have 1 plus y dash square minus y dash square y plus lambda equal to c1 under root 1 plus y dash square. So here we can take this y plus lambda out, so y plus lambda out, and inside you can say that it is 1 equal to c1 under root 1 plus y1 dash square, y dash square. So here we can say that y plus lambda is equal to c1 under root 1 plus y1 y dash square, so it is y dash square. So we want to simplify this. For simplifying this, we can introduce a new parameter t. So by saying that y dash equal to sine hyperbolic t, then y plus lambda can be written as c1 under root 1 plus sine hyperbolic square t can be written as y plus lambda equal to c1 cos hyperbolic t. So now we can find out, say, parametric representation of x, that is d of x equal to dy upon y dash, that is c1 dt, and we can say that x is equal to c1t plus c2. So taking t from this equation, we can say that t can be written as x minus c2 divided by c1. So y plus lambda can be written as c1 cos hyperbolic x minus c2 upon c1. So the shape of the hanging rope can be will be satisfying this equation, which is the curve which is known as catenary equation, and the constant lambda c1 and c2 can be obtained from the condition this and the boundary condition satisfied by the problem. Okay. So now let us also discuss a new problem which is known as finding the control which optimize a certain functional. So here the problem is as follows: find the control function ut, which is u1 to um transpose, which extremizes the functional which is known as performance index I, which is defined as 0 to t naught f naught x comma u comma t dt. Here x is a state vector given as x1 to xn transpose, and t is the time parameter, and t naught is the terminal time, and f naught is a given function of x comma u and t. And the relation between the control vector and the state vector is given by this equation, which is given as differential equation, and it is defined as dxi by dt equal to fi x1 to xn u1 to um. So your control variable and state variables are given by this, and we want to find out the control which extremizes the functional. So this is a very common problem in theory of optimal control, and we want to optimize extremize the corresponding functional this. So as in an isoperimetric problem, we introduce Lagrange multiplier lambda it and form augmented functional I star, that is given as 0 to t naught f naught plus summation I equal to 1 to n lambda I fi minus xi dash. So previous equation number 7 can be written as fi minus xi dash is equal to 0. So these can be considered as constraint given in terms of differential equation. So here we form the functional I star, which is given by this. Now here xi dash denote the derivative with respect to time t. Now here we denote this portion f naught plus summation I equal to 1 to n lambda I fi as h, which is known as Hamiltonian functional h. Now in terms of Hamiltonian functional h, we can rewrite this I star as 0 to t naught h minus summation I equal to 1 to n lambda I xi dot dt. So as we pointed out, we find out say Euler's equation, and Euler's equation is nothing but del h by del xi equal to minus lambda I dash for I equal to 1 to n and del h by del uj equal to 0, that is j equal to 1 to m. So what we did, we find out say Euler's equation for this, and which result in these n plus m equations. So the optimal solution for x comma u and lambda are obtained by solving the set of equation, that is 7, and the set of equation which we have obtained through the Euler's equation. And so these are in fact these are 2n plus m equation for which x, u and lambda I can be obtained. So if the initial condition xi's are given at n 0 and the terminal condition xj given at t naught are known, and if the conditions are less in number, we can always define lambda j at terminal say t as 0, and these kind of conditions are known as transversality conditions. So let us consider one quick example on this. So here we consider the example of finding the optimal control u, which makes the functional stationary with the condition that x of 0 is equal to 1 and dx by dt is equal to u. So control and state variable is related with this differential equation dx by dt equal to u. So here as pointed out, we can form the Hamiltonian function as h equal to x square plus ua square plus lambda u, and we can apply the Euler's equation, which is given in del h by del xi equal to minus lambda I dash and del h by del uj equal to 0. So if we do this, we have this equation 2x equal to minus lambda dash, which we get from equation number 11, and del h by del uj equal to 0, we will get this 2u plus lambda equal to 0. So here u is given as dx by dt. So if you use this and you can take out lambda here and put it here, and we can say that equation that state vector satisfy is this second order differential equation, and whose solution is given in xt of c1 sin hyperbolic t plus c2 cos hyperbolic t. Now c2 we can obtain by the condition which is given at x of 0 is equal to 1. So we can obtain by c2 as 1. So xt is given as c1 sin hyperbolic t plus cos hyperbolic t. Now we don't have any way to find out this c1 because x is not specified at the terminal point t naught. So for that, let us take lambda equal to 0 at t equal to 1. So this at once gives u1 equal to 0 because we have this equation 2u plus lambda equal to 0. So at t equal to 1, if lambda 1 is equal to 0, so u at 1 is equal to 0. So u at 1 equal to 0 means dx by dt is equal to 0 at x equal to 1. So so we can say that u equal to x dot, and we immediately get c1 equal to minus sin hyperbolic 1 divided by cos hyperbolic 1. So using this value of c1, you can write down the value of xt, and hence we can find out the optimal control like this. So ut is defined as minus sin hyperbolic t 1 minus t upon cos hyperbolic 1, and the corresponding state vector is given by x of t equal to sin hyperbolic 1 minus t upon cos hyperbolic 1. So here in today's lecture we have seen few things. First thing, we consider the variational problem with the, so variational problem means we have say y1 to say yn, which is given as say x0 to x1, f of x comma y1 to say yn, and y1 dash to say yn dash d of x, and we have considered the case when conditions are constant given in terms of finite equation, that is x comma y1 to yn is equal to 0, I is from 1 to say m, that we have discussed in previous lecture, and in today's lecture we have discussed the constant of the form given in terms of a differential equation like this, I equal to 1 to say m. and also we have discussed the principle known as a reciprocity principle, and with the help of reciprocity principle we discussed certain problem, and then as an example of this case we have discussed a case of optimal control, and here it is to be pointed out that this optimal control is not lying on the boundary of the set of admissible control. If it is, then we have a separate theory, not this theory will not work for the control which lie on the boundary of the set of admissible control. So here I stop, and we'll discuss next in next lecture. So thank you very much for listening us. Meet in next lecture. Thank you.